Hi everybody, this is Mustafa Kalami from Yarpaz, and in this video tutorial we are going to learn how to solve difference equations. Difference equations are very similar to differential equations, but they are defined in discrete domain. For example, this is a simple difference equation, xn equals to xn minus 1 plus 1. This is a simple difference equation. And if we solve this equation, we can get this solution, xn equals to n plus some constant. And this constant value is determined by having an initial condition. For example, if given that x0 equals to 0, then x0 equals to 0 plus c, and then we have c equal to 0, and the final solution is xn equals to n. You can create a sequence using this initial condition and using this equation. For example, if we have xn equals to xn minus 1 plus 1, and we are given that x0 equals to 0, then we can create a sequence of n and xn, n 0, 1, 2, 3, 4, 5, 6, 7, and so on. So we have x0 equal to 0, and according to this recurrence equation, we have x1 equal to previous value of x plus 1. So this is 1, this is 2, 3, 4, 5, 6, and 7. However, if we duplicate this slide and let's have another value for this, then we have a shift of 2 for values of this sequence, and we start with 2 and go on. So the general solution, xn equals to n plus c, holds for this, and they are same difference equations in the structure and recurrence equation, but with different initial values. You see that the concept is very similar to differential equations. However, how we can solve difference equations in the linear form of, for example, xn equals to alpha xn minus 1 plus beta xn minus 2. And given that we have x0 equal to some value, for example, let's name it x0 and x1. These are given initial values. How we can solve this equation? Just like the differential equations, we can express the solution of this equation as a linear combination of some fundamental functions. We can express the solution of this equation as xn equals to c1 and s1 to the power of n plus c2 s2 to the power of n. And c1 and c2 are determined according to the initial conditions. And n is the argument. And what are s1 and s2? S1 and S2 are the roots of this characteristic equation. S2 equals to alpha S plus beta. And this is very similar to the original equation. And we replaced xn with s to the power of 2, s squared, xn minus 1 with s, and xn minus 2 with 1. And you see that the power is decreasing as n decreasing. And this is the characteristic equation of this difference equation. And why this solution is acceptable for this difference equation? It's simple, because assume that we have a function xn equal to, for example, alpha xn minus 1. And the solution of this is generally in the form of s to the power n. Let's assume that that's a solution, s to the power of n equals to alpha s to the power of n minus 1. And generally, s to the power of n minus 1 is not equal to 0. So let's drop the s to the power of n minus 1 from both sides, and then we have s equal to alpha. So the general solution of this equation is alpha to the power of n. And this is an eigenfunction, in fact, like the exponent function, which is the eigenfunction of differentiation. And this function is the eigenfunction of differencing and time delay. So we can express the solution of this equation as a linear combination of two such eigenfunctions, and the base of these eigenfunctions are defined and are given by this characteristic equation. Let's write the characteristic equation, and this is the final solution. Let's solve for a well-known example. For example, assume the Fibonacci sequence, which is defined by f0 equal to 0, f1 equal to 1, and fn equals to fn minus 1 plus fn minus 2. So we can calculate the values of the sequence as 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. And let's solve this difference equation. This is a difference equation. And it has a mathematical solution, a closed form solution, and we can express every member of Fibonacci sequence in closed form, just having the n. Let's solve the equation. We have this equation, fn equals to fn minus 1 plus fn minus 2, and these initial conditions, f0 equals to 0 and f1 equals to 1. The characteristic equation is s to the power of 2, s plus 1. And the solution of this quadratic equation is given by s equals to 1 plus minus square root of 5 divided by 2. And we can express the fn by c1, 1 plus square root of 5 divided by 2 to the power of n, plus c2, 1 minus square root of 5 divided by 2 to the power of n. And now we must determine the values of these coefficients, c1 and c2. Let's use the initial conditions to solve for these. We have f0 equal to 0, and on the other hand we have this equal to c1, and if n is set to be 0, then this term and this term will be 1. So we can replace this with c1 plus c2. And f1 equals to 1, and this is equal to c1, 1 plus square root of 5 divided by 2 plus c2, 1 minus square root of 5 divided by 2. And now we have a system of linear equations of c1 and c2. From the first equation, we know that c1 equals to minus c2. And if we use this fact in the second equation, we can get that C1, 1 plus square root of 5 divided by 2 minus C1, 1 minus square root of 5 divided by 2, and we can simplify this as square root of 5 times C1, and this is equal to 1. So C1 equals to 1 over square root of 5 or square root of 5 over 5. And C2 is minus 1 over square root of 5 or minus square root of 5 over 5. And C1 and C2 are determined by this initial conditions. So the final closed form solution is given by this. Fn equals to 1 over square root of 5, 1 plus square root of 5 over 2 to the power of n minus 1 minus square root of 5 over 2 to the power of n. And this is the closed form solution of Fibonacci sequence. And you can test for other values. And for example, let's test it with MATLAB, for example. And we can set, for example, roots of the characteristic equation, as you know that we have this characteristic equation s2 minus s minus 1, and we can define it as 1, minus 1, and minus 1. These are the coefficients of the polynomial, and these are the solutions we have. And you can, for example, calculate the first root by 1 minus square root of 5 divided by 2, and this is the first root given by MATLAB, and this is the second root, and you see that both of them are given by MATLAB. So let's define the s as roots of this polynomial, and let's define the Fibonacci as function of n, which returns s1 to the power of n minus s2 to the power of n, s1 to the power n, divided by square root of 5. And we can get f0, and this is 0, f1, f2, f3, and we can modify the definition to vectorize it and have values. For example, the sequence from the 0th element to the 5th element, and you see that 0, 1, 1, 2, 3, 5, and you can get higher order elements from 0 to, for example, 10th, and you see that the Fibonacci sequence is given by this. And a well-known fact about the Fibonacci sequence is that we have this limit for Fibonacci sequence, that limit of fn over fn minus 1 while n approaches infinity is the well-known golden ratio. And here, using this closed form, we can prove this fact. And how? Let's use this definition. Let's duplicate this sequence, and let's use this definition. Limit of fn over fn minus 1 while n approaches to the infinity, and you see that this is equal to limit c1 s1 to the power of n plus c2 s2 to the power of n over c1 s1 to the power of n minus 1 plus c2 s2 to the power of n minus 1 while n approaches infinity. And you see that the absolute value of this term is less than 1, and the absolute value of this is greater than 1. So while n approaches to infinity, these terms are getting very close to 0, and the dominant terms which remain are the first term, and you see that C1 cancels the C1, S to the power of n cancels the S to the power of n minus 1, and just one S1 remains here, and we have S1 as the result, which equals to 1 plus square root of 5 divided by 2, and that's the well-known golden ratio. And this is a proof of this limit and the relation between Fibonacci sequence and golden ratio. Okay, generally you can solve this type of equations using the characteristic equation. For example, xn plus alpha n minus 1 xn minus 1. You can set alpha n here, and plus alpha n minus 2 xn minus 2, and alpha n minus k xn minus k equal to 0. And this difference equation can be solved using the roots of this characteristic equation. For example, the equation can be represented by alpha n s to the power of k, because we have k plus 1 terms here, and the greatest difference between these terms is k. S to the power of k plus alpha n minus 1 s to the power of k minus 1, and finally alpha n minus k equals to 0. And from this equation we get S1, S2, and Sk as our bases, and we can express the xn as linear combination of these bases to the power of n. So this is the final solution we get, and you see that we assumed that this equation has 0 on the right hand side, but in case that we have non-zero elements here, we must find a particular solution and add it to this general solution, and we get the final solution. However, we get there soon. But if these roots are not distinct, for example, assume that we have this equation, xn equals to 2xn minus 1 minus xn minus 2. The characteristic equation of this difference equation is s2 minus 2s plus 1 equals to 0, and both of solutions for this equation are equal to 1, and we have two solutions of order 1 for this, and we have two equivalent solutions, base solutions for this. So if we write the general form, we get C1 1 to the power of n plus C2, and this cannot be correct just because we set the 1 here plus C2 1 here, and is equal to C1 plus C2, and this cannot be correct. In this case of repeated roots, we convert this to C1 S, assume that both of them are equal to S, plus C2 NS. We multiply this by n, very similar to the technique we used in differential equations. And this is the general form, and if you replace S, you get C1 plus C2n. And this is the correct solution, and C1 and C2 are determined by initial conditions. Let's final solution for a given initial condition. For example, assume that x0 is 1 and x1 is 1, and then we have x0 equal to 1 equals to C1, and x1 equals to 1, and that is equal to C1 plus C2. Let's replace this with 2 to have a better solution. And here we see that C1 is equal to 1 and C2 is equal to 1. So the final solution is given by xn equals to 1 plus n. And that's correct. You can determine this with replacing these values here. For example, 2 times 2, 4 minus 1, which equals to 3, and that's the x2, and equals to 1 plus 2 and 3, and it's correct. Okay, if in case of repeated roots, you must multiply the roots by n. And if we have 3 repeated roots, then we must multiply the first one by 1, the second one by n, and the third one by n to the power of 2, n squared, and so on. And let's solve another equation in the form, for example, xn equals to 2xn minus 1 plus n, for example. You know that if we have not this term, let's remove this term and solve this. For example, xn equals to 2xn minus 1, and we can say that xn is equal to c times by 2 to the power of n. It is the general solution for this equation. Let's assume a given initial condition, for example, x0 equals to 1, but this cannot be the complete solution of this difference equation, and we must find a particular solution which is valid for this equation. This is known as general solution. We name it as x, for example, let's g of n. Let's name it as this. And finally, we get that xn is equal to xgn plus x particular and n. And this is the general solution, and this is the particular solution. And it is determined by assuming this non-homogeneous terms and finding some, for example, polynomials or other forms of solutions which is valid for this. Let's assume that xn and this particular solution is of the form, for example, a quadratic equation. Xn is alpha n squared plus beta n plus gamma. And we have that xn equals to 2xn minus 1 plus n. And this is our particular solution. Let's name it as Pn. And let's replace this definition here in this equation. Okay, alpha n squared plus beta n plus gamma equals to 2 times by alpha n minus 1 squared plus beta n minus 1 plus gamma plus n. And we have two polynomials in both sides of this equation, and the equality condition for two polynomials is that they have same degree and they have exactly same coefficients. So let's simplify the right hand side and get the final equations. If you simplify this, you get 2 alpha n2 plus minus 4 alpha plus beta plus 1 times by n, finally plus 2 minus 2 beta. I think we have a 2 here, 2 and plus 2 gamma, and okay, that's it. So must be equal to this must be equal to this, and this must be equal to this. So let's write down the equations. We have these equations: alpha equals to 2 alpha, and that says that alpha equals to 0. So we can remove alpha from everywhere. You can remove here, 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 and here. And beta equals to 2 beta plus 1. So beta equals to minus 1. And gamma equals to 2 plus 2 minus 2 beta equals to positive 2 plus 2 and plus 2 gamma. And sorry, this, if alpha is 0, then this term will be removed and we have this as this, and this says that gamma equals to minus 2, I think, and that's it. So we have the particular solution as x, p, and n equal to minus n minus 2. And you can test it. This holds for this general equation. And finally, we have the general solution of this equation, of this difference equation. Let's duplicate this. And you know that this is the general solution. And the final solution is given by xn equal to c times by 2 to the power of n. Particular solution minus n minus 2. That's we found. And if you want to determine the value of c, you can find it by this initial condition. So x0 equals to 1, and that is equal to c minus 2, and that says that c equals to 3, and the final solution is given by this. Let's write it here. Let's copy this. That's our solution. Final solution is given by xn equals to 3 2 to the power of n minus 2. And that's true. That's the actual solution of this difference equation. And you know that this is the general solution, and that's the particular solution. And that's the final solution we found for the difference equation. If the non-homogeneous term is polynomial, then the particular solution will be always of polynomial type, and you can find the solution using this technique we expressed here. I intentionally used the quadratic form, and that was not needed to have this form. Beta and gamma was enough. But sometimes you can get some difficulties if you assume the particular solution of lower order, and this may lead you to insolvable system of equations. So you can add some degrees, some extra parameters to your polynomial, and if we want to take safe side, we can start with a polynomial with higher order than this non-homogeneous term. The order of this non-homogeneous term here is 1, and we started with the order 2, with a quadratic term, just to take the safe side. Okay, for another example, let's solve problem with non-homogeneous term and some repeated roots. For example, xn minus 4xn minus 1 plus 4 xn minus 2, and all of them equal to n plus 1, for example. Let's find the general solution. The characteristic equation is given by S2 minus 4S plus 4 equal to 0. So both of roots are equal to 2. And we know that the general solution is given by C1 2 to the power of n plus C2 n 2 to the power of n. And this is the general solution. And what's the particular solution? Let's find that. Let's duplicate this and remove these lines. The particular solution is given by, for example, general form xpn equal to, for example, alpha n plus beta. And let's replace this in our equation. Alpha n plus beta minus 4 alpha n minus 1 plus beta plus 4 times alpha n minus 2 plus beta equals to n plus 1. So let's simplify these terms. So alpha minus 4 alpha plus 4 alpha times by n plus beta plus 4 alpha minus 4 beta minus 8 alpha plus 4 beta. These are equal to n plus 1. So this must be equal to 1 because we have 1 here, and this must be equal to 1 2 because we have 1 here. And let's recheck the equations to make sure that we have not any errors. Seems that it's correct. And let's solve these equations. Alpha minus 4 alpha plus 4 alpha, these terms are canceling each other, so alpha equals to 1, and finally alpha equals to 1, and we have equation here. Beta can add up these terms. 4 beta cancels this minus 4 beta, and beta plus 4 minus 8, which is minus 4, and equals to 1. So beta is 5. Alpha is 1 and beta is 5. And we have this final solution as xpn equals to n plus 5. And that's correct. So the final solution is given by this. Let's duplicate this slide. The particular solution is given by n plus 5. So the final solution is given by xn equals to c1 2 to the power of n plus c2 n 2 to the power of n plus n plus 5. And we need some initial conditions. Let's assume that initial conditions are given by x0 equals to 0 and x1 equals to 5, for example. And if we replace these equations, x0 equals to 0, and that's equal to c1 plus 5, and x1 equals to 5, and that's 2c1 plus 2c2 plus 6, and this gives us the c1 as minus 5, and this gives us the value of c2 as 9 divided by 2, or 4.5. So the final solution of this equation is given by these terms. I'll write down x for this initial conditions. xn equals to minus 5 2 to the power of n plus 9 divided by 2 n 2 to the power of n plus n plus 5. And if we simplify these equations, we can say that this can be stated as 9n 2 to the power of n minus 1 minus 5 2 to the power of n plus n plus 5. And it's the final solution of this difference equation, which has repeated roots in its characteristic equation, and it has non-homogeneous term at right hand side. And okay, it's done. I hope that this video was helpful for you. Let's know about your comments and feedbacks on our social media pages, YouTube or website of Yartest. Good luck.